Hi all, this is lecture 3. We are in section 2.3 and we are going to go back to those population models from section 2.1 and we're going to expand upon those. So the nice thing about the population models that we worked with in section 2.1 is that they were exponential. They just had the one term and it worked pretty nicely. And I believe at the end of that, we took a look at the density dependence, right? And we found that when we were, and this is kind of backtracking to section 2.1 so that I can build from there. So from section 2.1, when we had the recursive formula that PT plus 1 equals R times PT, if we solved this for what we call the parent to offspring ratio. So the parent generation is the previous generation, the offspring is the next one. So this is parent, this is offspring. So parent to offspring ratio means I want PT over PT plus 1. So I can do that here by dividing both sides by PT. So we have 1 equals R times PT over PT plus 1. And then to get that ratio by itself, we divide both sides by R. So I get 1 over R equals PT over PT plus 1. Now, when you start looking at our notes for this one, you'll notice that if I flip this around, this is PT over PT plus 1 equals 1 over R. Okay, and that was density independent, right? It did not matter. The parent to offspring ratio is not based on how many individuals are in the population. So how big your population does not affect how fast things are growing. But that's not necessarily true because in any given environment, there are going to be certain restrictions, right? Food restrictions, predator-prey interactions, climate and environmental nesting situations, right? All these kind of restrictions that are going to keep the population from just growing exponentially, right? There's not a bazillion squirrels in the middle of the quad because the environment doesn't support that, right? And so there's some kind of carrying capacity here is typically the term we use. That prevents our population from growing out of control. So what we want to do is we want to be able to incorporate that into our mathematical models. So what we do, you'll notice that in this next model, which we're going to call the Beveridge and Holt recruitment curve, you still have that same piece that we had for the exponential growth, okay? But then we're going to add this term here that has two features. Number one, it has a K in it, and K is going to be our variable for carrying capacity, or a parameter value letter for carrying capacity. And that's going to tell you kind of the ideal number, the ideal number of organisms that population, that climate area, that whatever their environment there is going to support, okay, for the given population. And it's also in terms of P. So now we have something that is density dependent. So that growth rate, that parent to offspring ratio, is now dependent on what our current population is, what that parent population is, which should make sense, okay? Problem with this setup, so we know that this setup is good in that the equation is going to be better. It's going to better model what's happening for us, which is great. Problem is that I can't use this in this format, right? Because what I want to do is generate my chart so that if I know what the current population is, I can make predictions about the future populations. But we're not set up for that. So what we want, just like up here, we had PT plus 1 equals something involving PT. I want to do the same thing here. So there's a bit of algebra to do here, and I'll walk you through it a little bit here quickly, and we'll kind of go from there. So what do we want to do first? Well, I've got a couple of issues here. So first of all, we've got the NT plus 1 is on the wrong side. So I want to kind of collect my PTs on one side and my PT plus 1's on the other. So that means I want to take this and I want to multiply it by PT plus 1. And I'm also, so let's do that in one step. Let's not go too crazy. So now we have PT, and I'm going to zoom in so that my handwriting is a little bit better for you. So PT equals PT plus 1. So I multiplied that over to the other side, or let's leave it this way. Yeah, let's leave it this way. So then we have the 1 over R plus 1 minus 1 over R over K PT. right? That's what was over there before, but we multiplied this side by PT plus 1. Okay. All right, now what I want to do is I want to get all of my PTs on the same side. So I'm going to do two things here. I'm going to flip this from left to right so that my PT plus 1's on the left. So I have PT plus 1 equals. And I'm going to divide both sides by this big term, the 1 over r plus 1 minus 1 over r kt k pt. Both sides. Okay, that's going to leave me with, now I'm flipping left to right, so PT plus 1 equals. And then I have PT over 1 over r plus 1 minus 1 over r over k pt. Okay, so there's some good things about what I've got going on here. I've got PT plus 1 equals and everything involving PT on the right. Problem is I got way too many fractions going on. I have fraction in fraction in fraction. So I want to clear some fractions out. So the first thing I want to do is I want to multiply top and bottom by k to get rid of this one and r to get rid of this one. Okay, so let's multiply top by r and k and the bottom by r and k. And that's going to help us to clear some fractions. Okay, so what does that do for us? We get PT plus 1 equals. Now I have r times k times pt in my numerator. Okay. On the bottom, some things are going to cancel. So I'm going to multiply this term times this term. So the r's will cancel, and I'm left with just k. Then I want to multiply this term and this term. And in this case, the k's will cancel, and I'm multiplying the r times what I have. So I'm going to have an r left over, and then I have the k cancels, so I have 1 minus 1 over r times pt. And then the last thing that I want to do here to kind of make this pretty is I'm going to distribute this r to both terms. So that's going to leave me with pt plus 1 equals r times k times pt up top, k plus, now when I distribute, this becomes r minus 1 pt. Notice that I'm not distributing the r to the pt, right? That's just multiplying it. I'm just multiplying the r inside the parentheses that I get rid of the r in the denominator there, okay? This is what we're going to use as our Beverton Holt recruitment curve. So when I use it in practicality, this is what I'm using. Okay, so there's kind of my whole process start to finish. So I'm solving the recursive function for pt plus 1. Now, when we use this, we're going to be given values for r and k. We're going to be told this is the replication rate, and so we're going to plug that in here and here. And then they're going to be told this is what your carrying capacity is, so we're going to plug it in here and here. And that will leave pt in your function so that you can start with whatever the original population value is, and that's where you're going to plug in your values to generate your population chart. Okay, we'll show you that in a little bit. All right, on to number 2. Here's where we're going to use it. So a given population has a carrying capacity of 30 and a growth rate of 1.5 and an initial population of 4. Find the first 10 values for the population based on the recursive function and sketch the graph. What happens to the population over time? Okay, so this is giving us information. So this is telling us that k is 30, that r is 1.5, and a, or what we sometimes call p0, either is fine, is 4. Okay, so that means when I set up my chart, and I'm going vertical this time, so t and pt, and I want the first 10 values, so 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 will give me 10 values. My initial at time step 0, I have 4. So the question is, how do I get the next one? So we're going to go back to that formula we had in the box. So this one right here. So r times k times pt over k plus r minus 1 pt. So let's start there. So we have pt plus 1 equals r times k times pt over k plus r minus 1 pt. Okay. And now we're going to plug in what we know. So we had that k was 30, so we're going to plug 30 in here. Our 1.5 goes in for the r's, and I'm going to subtract 1 there. So what we're going to do from there is plug those in. So this becomes pt plus 1 equals, my r is 1.5, my k is 30, and I'm multiplying that by pt. On the bottom, k is 30 plus 1 you're taking r minus 1. R is 1.5, so 1.5 minus 1 is just 0.5. So I'm just going to write 1/2 there. Okay. And then we can simplify that. 30 times 1.5 is going to be 45. So 45 pt over 30 plus 1/2 pt. This is our formula that we use to generate our chart. So if I plug my P0 in here for PT and simplify, then I will get the next P value. I will get the P1. Then I plug my P1 value in for PT, and that will give me my P2. Okay. Now I am going to show you how to do that. And the easiest way to do that, I'm going to go ahead and do that by downloading an app for you. So I'm going to, your best bet to, if you don't have a graphing calculator, is to go ahead and do that. So I'm going to go to the App Store, and we are going to download Calculate 84. There it is. It's the blue one over here on the top right. I've already downloaded it on my phone, so I can just download it here. It says it's intended for use alongside a TI-84, but essentially I think it's going to work just like a TI-84. So we're going to give it a second to go ahead and download or upload or whatever it is that we're doing at the moment. I think we're downloading. Okay, well, while it does that, we're going to go ahead and talk about what we're doing here. Okay, so while it does that, you're going to be doing that. So you're going to be plugging in the 45, so your P1 here. I'm only going to write out the first one or two. So P1 is 45 times P0, the previous value, over 30 plus 1/2 of P0. And your P0 is 4. So this is 45 times 4 divided by 30 plus 1/2 of 4. So let's see, that's 180 divided by 32, which we can get pretty quickly with any calculator. And we get 5.625. So that's my next population. Now, can you have 0.625 of an organism? No, really. So typically you're going to usually round these down because that's not actually 6, whatever you have, right? So typically with population, I would probably round down. But if you round up, I'm okay with that, right? Mathematically speaking, this would become 6, but that's okay. But we're going to add that to our chart. So that's my value, my p-value at time step 1, so 5.625. Okay. Now, my goal then is to find P2. And no, you do not have to write out your calculations like this. 45 times my P1. So P1 is the 5.625 over 30 plus 1/2 of 5.625. Make sure that you are using proper order of operations here. So we're going to take half of the 5.625, then add it to 30, and then take your fraction and divide it through. Okay, now we're getting into something where I don't have nice whole numbers to work with here. So let's see if my calculator has downloaded. Oh, nope, we're still only halfway. So we're going to let that one go for a few more minutes. Oh. Okay, and we'll start to get our chart, our graph ready. So we're going to, once we get these in here, we're going to go ahead and graph them. And you're starting down here at 4. And I'm going to kind of get to the punchline here. We're going to have 30 up here. 20 and 10. And what's going to happen when we get these values, you're going to see in a little bit, is that we're going to start at 4. We're going to increase quickly like we would for an exponential term, but somewhere in here we're going to start to level off. And it's going to approach 30 so that we don't go over that carrying capacity value. Okay. And that's what it's going to look like. And in a second, and actually I will just quickly give you these numbers and then I'll show you how I get them once the calculator app comes up. So what we're going to do on your graphing calculator is you are going to start by putting in the number 4, which is your initial value, right? So we're looking at the initial value of 4 goes into your calculator. There is then a store button. So it's STO with an arrow. On my graphing calculator is almost the bottom left button. So if you push that, and then you have to tell, we're trying to store 4 into a value for a letter. So I'm going to choose A. So you're going to hit alpha and the math button because it has a little green A up above it. And hit enter. It's going to output 4. All it's done is it's stored 4 under that value A. And then what I'm going to do is I'm going to go over here to my formula that's in the box. And I'm going to type this into my calculator using appropriate parentheses. But instead of using PT, I'm going to use A. So I'm going to open with, I'm going to have 45 times alpha A divided by parentheses 30 plus 0.5 times alpha A. And once I've got it in there, and again, I'll show you this in 1 second once my calculator app finishes. Oh, there it is. Here we go. Beautiful. So let's see if we can do it. So you're putting in 4. You're hitting the store button. And we're going to tell it where to put it. So I'm going to hit the alpha button and the math button to put in an A and hit enter. And that tells you you're putting in 4. From there, we're putting in our formula. So 45 times alpha A divided by parentheses 30 plus 0.5 times alpha A. Now, if you want to put the numerator in parentheses as well, you can. It's always a safer bet. In this case, we don't need it because there's no addition or subtraction. And we're going to hit enter. And there's our 5.625. And that's what we had already calculated. Now, here's where things get easier. So instead of having to do this every single time, all we're going to do is hit the store button right from where we are. And it's going to put in answer arrow. So it's going to take the 5.625 and it's going to store it where I tell it to go. Well, I'm going to replace my 4 with this new number. So I'm going to put in alpha A and hit enter. So now my A is 5.625. So now I want to plug this into my formula as the A. Well, there's a shortcut to do that. So if you hit the second button and then up above the enter button in the bottom right corner, it says entry in blue. You're going to hit that. And hold on. Oh, wait, I'm sorry. Back the train up. You're going to hit the second button and the enter button. That's going to give you whatever you entered last. I don't want that. I want what I entered 2 times ago. So I'm going to hit second enter again. That's going to go back to the thing you entered 2 times ago. You can actually do this up to 10 times. It stores your last 10 entries and will take you back through them. But I want the formula, so I'm going to hit enter and I get my next number. So 7.714. And I'm just going to keep maybe 2, 3 decimal places. So let's just keep 2. Let's go to 7.71 and add that to my chart. Then I'm going to go back to my calculator. I'm going to hit store alpha A. And then I'm going to go back to that function. So second enter, and enter again. And I get 10.25. And I'm going to keep doing this over and over again until I get all the values that I need. So store an alpha A, enter, second enter, enter, 13.14. And this allows me to keep particular values so I don't have to round and use rounded values. But I don't have to type it all in. And that's what's super nice about this. So store alpha A, enter, second enter, enter again, 1616. Store alpha A, second enter, enter, 19.1. Store alpha A, second enter, 2173. Store alpha A, second enter, 2393. Store alpha A, second enter, enter, 25.67. Okay, and you can kind of see that the numbers are showing you exactly what I was showing you here on the right. So if we had graphed these from 0 to 9, you'll notice that these numbers are approaching 30. Now, we didn't go far enough to see it level off quite that way, but the same thing is true. Okay, now what I want to do is I want you to hold off on problem number 3, because I want to do this one in class with you, and I want you to see that on Excel so that we can kind of see what's happening there. So I think we're actually going to hold off and stop our video here. So we've got our new model, we've got our Beverton Holt recruitment curve, and we've got our example of how it works. So from there, in class, we'll take a look at using Excel to kind of show you what the graphs look like. And then we're going to say, okay, do we need to talk about a new model? So we're going to end things here.